I'm Lauren Bennett, and this is my colleague Flora Vale, and we are going to be talking about regression analysis this morning. I am a product engineer on the spatial statistics team in Redlands, so we work on the development of the tools that we'll be talking about today, that we talked about yesterday, that we'll be talking about tomorrow, all those fun spatial stats tools. Flora is out of our DC office. She works with a lot of our health customers, but is also an honorary member of the spatial stats team and plays a big part in us designing and implementing these tools. So we are really excited to get a chance to talk to you about regression analysis today. I guess I will say that obviously whole college courses are taught on regression analysis. You could actually get an entire degree probably on regression analysis. We have 75 minutes. So I would say don't worry about it, memorizing everything that I say. It's just kind of come along for the ride. And our goal is that for those of you who, how many people in here do regression analysis on a regular basis? Awesome. So for you, my goal is that you walk away with an understanding of how regression analysis is implemented in ArcGIS and how these tools work within the context of ArcGIS. And for those of you who didn't raise your hand that you don't do regression analysis on a daily basis, that's totally okay too. Our goal is that we get you excited about regression analysis, maybe convince you that you too can do regression analysis every day. So I'd say there's kind of something for everybody here. So today we're going to talk about ordinary least squares regression, which is one of the regression analysis tools in ArcGIS. It's kind of the de facto standard regression analysis method. It's been around for a very long time, and it is a really powerful regression analysis tool. And we're going to talk in pretty great depth about what we call the 6 checks. These are the underlying assumptions of ordinary least squares regression. These are the things that you need to do in order to feel confident that the regression analysis that you're doing, that the model that you found, the variables that you found is a model that you can trust. So we're going to talk about those 6 checks quite a bit. We're also going to talk about geographically weighted regression, and geographically weighted regression is kind of the next step in the process. It's a really powerful tool that essentially it's where we bring space into the mix and we really start to take advantage of the spatial nature of our data so that we can use that to our advantage when we're making decisions and we can really focus our resources. So we'll talk about geographically weighted regression too. So before we jump into this, we're really going to talk about regression analysis all in the context of an example. It's a demo scenario using real data that we're going to use to walk through the whole regression analysis process. So to start, Flora is going to set the context for the analysis that we'll be using the whole time.
Okay, can you guys hear me all right? Doesn't seem as loud to me, but I guess
is that good?
Yeah. Good. Okay, thank you. Okay, so what we're looking at here is a map of hospital or of Medicare spending per capita, and these are hospital referral regions. And so this is a hotspot map, and it has identified some clusters of high and low values. Over here we see that we have a cluster of high Medicare spending per capita. Over here some lower values. But ideally we would be spending about the same amount of money per Medicare beneficiary no matter where we were looking, right? But it seems like this is not really the case. So we want to know why. Why do we spend more on Medicare in some places than in others? So the first thing we decided to look at was, well, maybe the people in those areas where we're spending more money, maybe they're getting better care, and better care costs more money, so that's what's happening.
Yeah. It was a little naive, but we figured we'd try.
We had to check. And one way to check that is to look at hospital readmission rates. So hospital readmission rates are a common measure of quality of care. The idea being that if you are readmitted to the hospital within 30 days of being released, if it's the same condition, then you didn't receive adequate care in the first place, which is why you had to return. So This is a hospital referral region map of hospital readmission rates, and I'm actually going to go to the effects toolbar here so I can do a little swipe and take a look at how these two maps compare. So, you know, it's kind of obvious, even just with a visual analysis, that the people in that area are not, in fact, getting better care. That it's actually darker over here, meaning that the readmission rates are higher, so they're actually getting worse care. So we're still left wondering, why do we spend more in some areas than others? And if you hadn't guessed it, we're going to try to answer that question using regression analysis, and Lauren will tell you a little bit more about that.
So we are going to answer that question using regression analysis, but before we do that, I want to get us all kind of on the same page about regression analysis. Some of us in here are experts. I'm sure there's a couple of you in there that know significantly more about regression analysis than I do. And then there's others who maybe have never done it before. So we want to get kind of speaking the same language about regression analysis. So regression analysis is a set of methods that are used to model, examine, and explore relationships to better understand the factors that are behind observed patterns in our data. It's when we ask these why questions, right? We want to understand why so that we can do something about it. When we see a hotspot map of Medicare spending, we're not satisfied to know where Medicare spending is higher. We want to know why so that we can lower spending in those areas and save money and give people better care. Of course, we can also use it to predict outcomes based on that understanding. So if we know that certain factors are related to the variable that we're interested in, we can use that to predict what impact would changing some of these underlying factors have on the thing that we're interested in. And so it's really this way that we estimate relationships between variables. And this is a simple scatter plot of just looking at two variables, but those same kinds of ideas apply. It's about these relationships that exist in our data. So we can use regression analysis for really kind of three reasons. The first one is about exploring correlations. And we kind of think about this as like casual correlation exploration. We're just looking for these casual correlations. Now, that can be really powerful, and we do it all the time. We've all made a scatter plot at one point or another or looked at them. They can be very powerful, but we do have to be careful when we think about exploring correlations. For instance, we can see that divorce rate in Maine versus per capita consumption of margarine appear to be very highly correlated, which must mean we should stop eating margarine or people should stop getting divorced. I'm not sure, but either way, clearly these two things, hey, maybe they are related. Or even better, the number of people who drowned by falling into swimming pool versus the number of Nicolas Cage films. Still a pretty high correlation. I mean, these things are ridiculous, right? So we do have to be careful when we talk, these correlations can be very powerful, but we do want to do more than just explore casual correlations. And that really is why the 6 checks are so important and why we're going to spend 8:30 on a Wednesday morning talking about it. This is just kind of a funny, I don't know if you guys know, how do you say that?
XKCD.
XKCD. I used to think correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe. Can't say for sure. Sorry. So those are the casual correlations. We are friends in real life, and these are the kinds of like messages we send each other, like on a Friday night. Look at this really funny, stupid correlation I found. We're really big nerds. So regression analysis and why we use it. We can talk about exploring correlations, and there are tools to do that, and certainly regression analysis does allow you to do that. But we do want to go beyond that. We can also use regression analysis to predict unknown values. Like if you think about an example might be you have rain gauges in certain places, but there are some locations where you don't have them. If you know the relationship between how much it rains and other things like elevation, temperature, those sorts of things, and you have locations where you have no rain data, you could use a strong model with a good R-squared to predict rainfall in places where you don't have any data based on all the other variables that you have that you know are related. So predicting unknown values can be very powerful. But the reason that I think both of us get excited about regression analysis and the reason that the 6 checks are so important is because one of the really powerful things that we can do is we can understand the key factors that are underlying these processes. And by understanding those key factors, by finding a model that we can trust, we can feel confident that the relationships that we find are real and that we can actually use that information to guide decision making and make decisions that will actually improve whatever it is that we're trying to learn more about. And before we go on, we know that we only have 75 minutes, so we of course start with data that's already ready to go for our demos and our analysis. But data in real life is messy, and I do just want to take a minute to talk about this idea that we often find ourselves dealing with data that is either missing or suppressed. Oftentimes we work with health data, and health data, it's very common to have areas where data's been suppressed for one reason or another, or just missing data in general. And one of the ways that you can deal with missing data that is a tool in ArcGIS is by interpolating missing values. There's a new tool out in, I think it came out in 10.2, called aerial interpolation. Aerial interpolation is a tool in the geostatistical analyst toolbox. And aerial interpolation essentially allows you to interpolate based on a set of polygons, create a continuous surface that also has an error associated with it, so you know the confidence that you have in those predictions, and then it allows you to put that data back into your polygons, where you have any polygons that kind of fall inside of that surface. So just something that I think is very valuable it's kind of in a different, it's in a different toolbox, and it can be used for different reasons, but for the work that we're doing, especially with regression analysis, where it is important to have all the data in all the places, you can use these, and I just think it's important to kind of take note of it. So now we're ready. We've got all our data. It's filled in. Now the fun starts. So this is where some of you want to get up and leave. Some of you are thinking about throwing something at me. It's like, why did I choose this one? But we're not going to talk really about the equation. The equation is just a valuable way. It provides us with context to just go over some vocabulary so that we're all on the same page. Because actually, this equation is at the heart of regression analysis. And while we don't have to understand the math, it's really not what it's about. We can use this to understand what regression analysis is all about. So we start with that y. That's what we call the dependent variable. That's the thing that we're trying to model or explain. It's what are we trying to predict or understand. And we can see it's on the left side of the equation, right? So we want to say y equals something based on all these other things, right? So that's the thing we're trying to predict or understand. Then we have all those x's. Those are what we call explanatory variables. Now, the explanatory variables are the things that we believe cause or explain or are related to the dependent variable that we're trying to model. These are also called independent variables. Now, explanatory, I think, is a much more, it's a word that means what it says. They're just the variables that are trying to explain your dependent variable. So very simple. We have the y's and the x's, and we can see that the x's are on the right side of the equation. They're the things that are being used to figure out what y is, what our dependent variable is. And then we have the coefficients. And you'll notice that those coefficients all fall next to one of our x's. And that's because the coefficients represent the relationship that each x has to y. So, for instance, Nicolas Cage films would have a positive relationship with people drowning in pools, for instance. I don't know, whatever it said, or margarine and divorce rates, positive relationship, apparently. But in real life, if we were talking about Medicare expenditure, we might expect, for instance, a positive relationship with we would expect a positive relationship that as Medicare spending goes up, what's a good one? Yes, that would be a negative relationship. I could think of a million negative, but for some reason the positives seem difficult. The health of the population would go down also. Anyway, you get the picture. Here, as obesity rates rise, we expect diabetes rates also to rise. So that's a good example of a positive relationship. Or a negative relationship would be, as foreclosure rates rise, we would expect home values to be dropping. Or in the case of the Medicare expenditure, Medicare spending goes up, we expect quality, we see kind of that we're seeing quality of care go down, for instance. Or where we have no relationship and that the value for X is not correlated with the value of Y. And it's these all fall with that funny looking B symbol in the equation. Those are the coefficients. If it's positive, if it's a positive number, it means there's a positive relationship. If it's a negative number, it means there's a negative relationship. And that's what the regression analysis is all about. These coefficients, we spend a little bit more time talking about them because they are kind of at the heart of what we're trying to do. We want to understand those relationships because that's what we're going to use to make decisions. And then finally, we have residuals. Residuals are the model over and under predictions. So essentially, when we create a model, we are creating this predicted line, and it's based on all of those values that we know. And so what we can see, we have a predicted value and we have an observed value. We know the true value of Y, and then we have the value of Y that we predict based on our regression model. And when the true value is less than the predicted value, we have an over prediction. When it's greater, we have an under prediction. And what we want, and these over and under predictions are the error. That's that error term, and we call it a residual. And we'll talk about how those residuals are important to us, especially in thinking about the 6 checks. So that gets us on the same page. We've got dependent variables, explanatory variables, coefficients, and residuals. That's really all there is to regression analysis. And so we're going to talk about, Flora is going to show us how regression analysis works inside of ArcGIS.
Okay, so for this analysis, we're actually just going to focus on that hotspot of high spending down here in the south. So we see here that even within this cluster, we have quite a bit of variation, with some of the referral regions spending as little as about $7,500 per Medicare beneficiary, and some of them over $14,000. So what we're trying to explain here is that variation. What causes variation in Medicare spending? So do you guys have any ideas of what might cause variation from one place to another? Age, yeah. Anything else? Cost of living, yeah.
Nutrition.
Yeah, the health of the population.
Lifestyle. Oh, supply of services.
Yeah, access to care. Yeah.
We've got a pessimist in the audience. A realist?
Yeah, that's true. Well, I'm sure that those all might play a role, but the first thing that we thought, again, maybe naively, was, well, maybe the people are just sicker here, so it's just more expensive because we have to take more care of them because they're sicker. So a common measure of the health of a population is an HCC score, which is an index that kind of measures the prevalence of chronic conditions like diabetes, heart disease, that sort of thing. And so I'm actually going to run ordinary least squares regression against HCC scores to see how well that variable explains Medicare spending. I'm going to go into the Spatial Statistics toolbox, into the Modeling Spatial Relationships toolset, and open up ordinary least squares. And for any of these tools, you don't really have to remember what toolbox they're in. You can just use the search window, which is where I usually get all of my tools from. But I just wanted to show you that they're available in the toolbox. So our input feature will be that study area. I'll give it a unique ID and then name this. So our dependent variable, again, that's what we're trying to explain. So that will be the total costs. And then the explanatory variable that we want to test in this case is average HCC score. So I'm going to go ahead and run that. All right, so this results window is really helpful because it gives you a summary of the results. And we can see here, the first thing that I want to look at is that adjusted R squared, and that's 0.65. So If this model was properly specified, that would mean that HCC scores explains about 65% of the variation in Medicare spending, which is actually pretty good. But like Lauren mentioned, it's not quite that simple. So we're going to have to check some other things. One of the great things about running ordinary least squares inside of ArcMap is that it gives you a spatial output. So this is actually a map of the residuals, those over and under predictions. So no model is perfect. We're always going to be a little bit higher over here, a little bit lower over there, but you would expect that to be kind of random, kind of just spatially random. But we can see here that the over predictions and the under predictions are obviously very clustered, right? So
although this map is just, I can't believe how bad these projectors are. It's crazy, but it's really blue.
It's really blue over here and really red over here. So it's pretty obvious, and I'm sorry that you can't really see that. But in this case, we know that there's something else happening. We're missing some key explanatory variables that are causing our residuals to be so clustered. And in this case, I'm not even going to test it because we can just tell by looking at it. But there are 6 other checks, and this model is not going to pass. So we actually did come up with a properly specified model, and I'm going to run that one. So again, our study area, ID, dependent variables, total costs. And what we found to best explain Medicare spending in that area was the number of hospital beds, readmission, evaluation and management. Mm-hmm. These are out of order, yeah. Imaging events like MRIs and CAT scans, that sort of thing. Distance to Houston, which is a spatial variable that Lauren will talk a little bit more about in a minute, and dehydration rates. And I'll go ahead and run that.
So one thing that you'll notice is a lot of the output here is in the messages window. And how many of you turn off the background geoprocessing when you're running the geoprocessing tools in ArcGIS? But for those of you who don't turn off background geoprocessing, you're really you don't have to turn it off. You can get to the messages window from the results window, but a lot of the critical output of ordinary least squares regression is this numeric output. And we're going to talk about it, so don't worry if that looks like gibberish right now. It will all make sense by the end. But it is important to note that there is a lot of output there.
Yes. Okay, so now we can see that our adjusted R squared has gone up to 0.86, which is really, really good. And we can see here that our residuals, I can see here that our residuals are not obviously clustered, but it's really hard to tell with a visual analysis. So I'm actually going to use another tool in the spatial statistics toolbox. Spatial autocorrelation to test the clustering. So we'll put our results in there, and we'll see if the residuals are clustered. And I'm going to generate a report so that we can interpret the results of the tool. All right, so in the results window, I'm going to open my report file. And it gives us this little report here that tells us that the residuals are not clustered. They're spatially random. If they were clustered, then they would be over here on the right side of this tail, and the clustered box would be highlighted. So you really don't even have to understand what's going on. The picture explains it for you. So we have a good R squared. Our residuals are not clustered, but there are a few other checks that we need to go through. So we're going to go back to the slides to talk about those.
So Flora was talking about the fact that we had found this properly specified model, and finding a properly specified model isn't magic. It is usually the result of an iterative process, a little hard work, some research, probably a dash of luck in there somewhere. And It's also the result of these 6 checks. It's really these 6 checks that allow us to feel really confident that the model that we find is valid. So we want to go through each of those 6 checks. So the checks start with talking about the coefficients. There's a couple of checks that are related to our coefficients and to those explanatory variables that we've included. So check number 1 is that each explanatory variable should have the relationship that we are expecting it to have when we do this analysis. So when I was working on my master's thesis, one of my advisors, who's Lauren Scott, who is also on the spatial statistics team and actually wrote all these tools originally, she was tough. And so I had a bunch of variables I wanted to include. And she said, okay, yeah, these are all great, but before you include them, I want to know why you're including them. What relationship are you expecting each of these variables to have? And so what you want to do when you run this analysis is check that each one of those coefficients has the relationship that you're expecting. So does a variable that you're expecting to have a positive coefficient actually have a positive coefficient? Now, that's not to say that sometimes you won't be wrong. It is possible that you are expecting a relationship and you're wrong, but it's only if you go through this check that you'll even catch that. Because, for example, I was looking at childhood obesity, and I included a variable that was no education. It was a no education variable, like not any education in any school system whatsoever. And I was thinking of that as a variable that was about education. But when I did my analysis, it actually turned out that obesity rates were lower. There was a negative relationship. When this no education variable went up, obesity rates went down. And so then I had to really reevaluate, well, what does this variable actually represent? And what I found was that it actually really represented the immigrant population, people that had come to the country, educated elsewhere, and just no education in the U.S. school system. And so actually, these are people that were feeding their families really well, and obesity rates were lower in these areas. But it was only because I had done that kind of due diligence in the beginning to really think about what relationship I was expecting, and that I really evaluated the outcomes, that I was able to kind of really understand what that variable meant. So it is really important to have this idea of what to really meaningfully select the variables that you're including, not just throwing everything in the kitchen sink. So the second check is you want to make sure that each variable is statistically significant. So essentially what you're trying to do is make sure that each variable is telling an important part of the story. If we're doing a regression analysis and we have an R-squared that says that's 0.86, I kind of think about it like we're telling 86% of the Medicare spending story. So we want to make sure that each one of those variables is telling an important part of the story. And we do that by checking if it's statistically significant. And that is really easy to do. All you have to do is look for these asterisks. Do each of the explanatory variables have an asterisk next to those probabilities? If those probabilities have an asterisk next to them, then we pass the check. In this case, we pass the check. We just look for the asterisks. So the next one is actually about the residuals, and it's something one of these is something that Flora already talked a little bit about. So the idea is that our residuals should not be clustered in location or in value. And we've talked a little bit about our residuals not being clustered in location. We want to make sure that our residuals don't show any spatial autocorrelation. And we don't just have to trust our eyes, because that can be quite difficult, especially when you get into kind of the gray areas. So we can use the spatial autocorrelation tool to make sure that those residuals aren't spatially autocorrelated. And the little report will literally just answer the question for us. So in this case, they're random, and we pass check 3. So the next one is about making sure that our residuals are normally distributed. Now, if you think about it, if our residuals were random, we expect the residuals to be random. Those errors. We want the over and under predictions to have really a random distribution. So what that means, if they really are random, we expect most of them to be pretty close. We expect the most of them to be close to 0, close to a good prediction, right? Close to the you want the distance between the predicted value and the expected value to be small, and you expect most of them to be in there, and then less of them to be a little bit bigger, less of them to be a little bit bigger, less of them to be a little bit bigger, and that creates a normal distribution starting at 0. So you want a normal distribution where the average is in that 0 range. So there's a simple test for that. It's called the I don't know how simple it is under the hood, but the checking to make sure if your residuals are biased in some way where they're not normally distributed is very simple. There's a test. It's called the Hark-Barra test. And all you want to do in this case, you want to make sure that the Hark-Barra statistic does not have an asterisk. So for the coefficients, we want them to be statistically significant because it means that they're telling an important part of our story. But with the Hark-Barra statistic, if that had an asterisk, what that would be telling us is that our model is biased. When there's no asterisk, it means that our model is not biased and we can trust we're getting closer to being able to trust our results. So we don't have bias. Now this can actually be one of the trickiest ones. And one of the things that I would say is that, and actually I want to say two things. One, for the Hark-Barra statistic, if you're running your analysis, and we're going to talk a little bit about how we found that model, but I can tell you, no matter how awesome the tools are, that it's always going to be an iterative process. If you run a regression analysis on the first try, have a perfect, properly specified model with a high R-squared, congratulations. But I think most of us know that it's not usually that simple. There is always iteration. We learn something every time, and it is always this process, but you will find yourself looking at a model that is not properly specified at one point or another. I can promise you that. So one of the things that I've found is that this can be one of the hardest checks to really meet, to get rid of the bias in your residuals. And one of the things that can really help here is transforming your variables. So if you're finding that you're having trouble with biased residuals, what that can often mean is that some of the relationships between the variables in your data are not linear. Now, if they're not linear, like for instance, looks like this instead of like this when you look at it on a scatter plot, all you have to do is a log or square your variable, and you can change the shape of that line. And when you do that, you're still using the same variable. It's just that by logging it or by doing some sort of a transformation on that variable, you can get rid of some of the bias in the residuals. So that's one of the kind of tricks that we actually talk about in a lot of the documentation. We have a whole document about what to do when regression models go bad, and this is one of them, and we have some tips for what you can do if your residuals are biased. So another important check is about the variables and the idea that each variable needs to be telling an important part of the story, but you also want to make sure that each variable is telling a different part of the story. So a really common way that this is explained is often using the idea of modeling home values. So if you're modeling home values and you include one variable for the number of bedrooms and another one for square footage, oftentimes what we find is that those, not all the time, not in every place, but in a lot of circumstances, square footage and number of bedrooms are getting at the same thing. They're telling the same part of the story. How big is the house, right? And so we include these two variables, and they're both telling the same story, and that can cause instability in the model. And so you want to make sure that your variables are all getting at a different aspect of the problem that you're trying to model. And so we have this test. It's the variance inflation factor. It's a VIF. We create these VIF values. And what you're looking for is a VIF value lower than 7.5, but really the lower, the better. What you do if, for instance, your VIF values are high, you won't ever just have one VIF value be high, since it's about models telling the same story. This is a measure of it's a wonderful statistics word called multicollinearity, which just means that your variables are telling the same story and that they're redundant, essentially. And so if you have redundant variables, what you're going to want to do is you see the ones that have high VIF, get rid of one, try running it again. And what you'll find is that you won't lose a lot in your model because they're telling the same story, right? So you get rid of one, run it again, see how the model performs, then try ripping out the other one, putting that one back in. So you try both and see which one to keep. I just want to make sure we get through all of the, but I promise afterwards. Thank you. So using the VIF values to figure out, it's not like get rid of them both, right? One of them might be really important. You just pick the one that actually helps the model more. So in this case, all of ours were well under 7.5, so we passed this check too. We're doing really well. I often lament in this workshop about how when I talk about my thesis like it was really awesome, but it was really horrible. And the highest R squared I ever got was like 0.5, and that was after I am talking about months of just painstaking work. And so we ran this and we found a model, I don't know, in like 2 weeks. It's like I totally picked the absolute wrong topic. I should have just done this all along. I'm always so upset when I give this because it's not fair. So we passed this check too. So the last check is about model performance. And how many people remember regression analysis, and the only thing they really remember learning about regression analysis was an R squared? It's all anyone talks about. You read the papers, most of the papers most papers even mention R squared. Oh, well, I have high R squared, but we just went through all those checks. The reason we put this check last is because it doesn't matter how high your R squared is. If you're not meeting all of the other assumptions of OLS, you can't trust it. It's like the 0.99 R squared for the margarine and divorce rates. Yeah, it's a really high R squared, but I guarantee that would not be a properly specified model. So we put this last, not because we look at it last. Obviously, when we run a regression analysis, even I look at the R squared first. I want to see what my R squared is, but I can't really trust it until I go through those 6 checks. So we do try to de-emphasize it a little bit. And the other thing about R squared is this is the only one of these that is completely subjective. What is a good enough R squared? It depends on the field. It depends on what you're researching. In anything where you're talking about predicting human behavior in any way, 0.5, 0.6, you're golden. I mean, I would have been doing a dance if I had seen a 0.86 in my work on childhood obesity. But if you're talking about, medicine, drugs, 0.86 isn't high enough. It's got to be like 0.99999. You need to be basically 100% sure. You need the highest R squared possible. So it just really depends on the field, on the topic, on the research. And you have to, my best advice in there is to understand for whatever it is that you're researching, what the literature kind of is, what the threshold is that people are meeting for something to be considered important. But for us, we thought 0.86 was pretty darn good here. So we were happy that we passed this check. So we passed all 6 checks. I do want to make a point that the online help is helpful. It's hard to believe, but Lauren Scott, who I mentioned was on my thesis committee and is also one of my closest colleagues on the spatial statistics team, I can say this because I'm not the one who wrote the doc. She has written the most amazing documentation on regression analysis that I think you'll find anywhere. The regression analysis basics documentation, which is just one of the kind of learn more about regression analysis in our standard documentation in the help, is one of the best documents you'll ever read about regression analysis. If you walk away from here thinking, I have no idea what she just said, just read that document, and it's where she's amazing at explaining these things, and I really recommend if you find yourself kind of stuck in the process, go through that documentation. There's a lot of tips and tricks and best practices in there. There's also that table that I was talking about, which has common regression problems, consequences, and solutions. So we talk about what's the problem, why is it a problem, and then what do you do about it. So a great example would be you have a biased residuals. Why does it matter that your residuals are biased? What do you do about it? So I do really recommend the online help. Okay, so here is a little secret. We always do this regression analysis workshop and we show this model that we found and we're like, we're so amazing. We found this great model and it was magic. But the truth is it's not magic and it's really quite painful to find one, or it used to be a lot more painful. It was actually while working on, when I was doing my analysis on childhood obesity and I was having such a hard time, we started there, exploratory regression started as this really crude sample script that our developer wrote for us to help us find models. Then it evolved over the course of that into this incredibly powerful tool that will help you not just find a properly specified model, but also just explore relationships in your data. I think exploratory regression is just a really fun tool to play around with if you want to learn all about the relationships that exist in your data. There are trade-offs. Yes, you'll learn a lot about relationships. So essentially what exploratory regression does is it looks at each variable. So you say, here's my dependent variable. Here's all of the explanatory variables I'm interested in. And it tests all the different combinations of those variables. It's kind of like a stepwise regression analysis, except stepwise regression focuses on R squared, and exploratory regression actually checks all 6 checks. It checks all of the underlying assumptions of OLS. So it is quite powerful. There are trade-offs, though. A lot of the things in here, we're looking at probabilities, right? And probabilities are telling us, so if you have a 0.01 probability, what that's saying is essentially 1 out of 100 times this could be wrong, but we're saying it's right. 1 out of 100 times. Now, if you do that 1,000,000 times, because you've tried all these combinations, 1 out of 100 becomes actually a lot bigger number. 1 isn't 1 anymore, it's bigger. So that there is this increased risk for type 1 statistical error, but the truth is that we're always trying a lot of different combinations. We're doing regression analysis anyway. We go in. We kind of would recommend, I think, it's certainly not a conservative. We're kind of middle of the road. I think our advice would be, don't just throw in every single variable. Really have a reason for the variables that you're including. Somewhere in between just the everything but the kitchen sink, and I'm going to test these 5 variables exclusively, and that is it, and then I will, if this doesn't work, then I'm not doing a single other analysis. Somewhere in the middle there where you're really thinking, you're basing the variables that you include on logic and reason and research and expert opinions and all of those things. Exploratory regression can be an incredibly powerful tool. And it's not just for finding properly specified models. So Flora's going to talk a little bit about, she's going to show us exploratory regression, the magic behind us finding a properly specified model.
All right, exploratory regression is actually one of my favorite tools, so let's take a look.
Obviously, we send like XKCD cartoons to each other on Friday nights.
So again, we'll have that same dependent variable, the total spending, but now we can just add all the different variables that we have in that layer and have the tool check for us all the different combinations and test those 6 checks to see if we have any passing models. So I'm just going to select all and then take away a couple of the things. We don't want to use total costs to explain itself, so I'll uncheck that. And then we don't need things like shape, area, and length, IDs. Now I'm also going to save a output report file so that we can take a look at the report, the results. So save that and run. So this is another reason why it's really great to have the geoprocessing in the foreground, because you can actually watch as the tool works. And sometimes if you throw a lot of variables in there, it can take a little bit longer, but I always start just scrolling up and seeing like if anything has passed already before it makes it through all the rest of them. There's a lot of really great information in here. I'm going to open it up actually in the report so that we can see it a little bit easier. So again, in the results window, my report file. Expand this a little bit. So like Lauren said, it goes through every combination. So first it's going to check one variable at a time. And then it's going to check every combination of 2, 3, 4, up to 5. And if you have any passing models, it'll say that under the passing model. So we see here that for 1, It gives us the result of the highest R-squareds, but under passing models, we don't have anything because nothing passed with just one variable. Same with 2 and 3. At 4, we start to get a couple passing models, and then at 5, we have some with even higher R-squareds. So the best passing model with the highest R-squared that passed all the other checks was that one that we looked at earlier when I ran ordinary least squares. So the hospital beds, evaluation and management, imaging, distance to Houston, and dehydration. So even though exploratory regression is one of my favorite tools, it's not really just that easy. It's still an iterative process, and you can still have to run this many, many times in order to find a properly specified model. And it can be kind of frustrating sometimes when you don't find one, but this actually gives us lots of other helpful information that can guide you towards finding that properly specified model. So if we look down a little bit further, one thing that I always check, which is really helpful, is this summary of variable significance. So it's actually going to tell me how often one of these each variable was significant, and then how often it was a positive or a negative significance. So we see that, imaging was significant 100% of the time, and 100% of the time it was positive. So I know that even if I'm not getting a passing model, I should probably keep that in my analysis. But something like percent asthma, that's only significant 50% of the time, and it's not always positive, I might consider dropping that one if I'm not finding a properly specified model. So there are other things too about, the other 6 checks, but we'll talk about those actually in our workshop this afternoon in more detail. So if you'd like to learn more about that, a little plug for our other workshop.
So that's exploratory regression. Even if you're not looking to find a properly specified model, we often use exploratory regression for all sorts of reasons, just to learn about those relationships, which Flora will talk about a little bit more also which we'll talk about more in the next workshop. But it's just a really kind of fun tool to run just to see what you find, if you like things like that. So we're finally at the point where we've found a properly specified model, and we're ready to move on to geographically weighted regression. So I know some of you are like, I've been here for 45 minutes, we went through that whole thing, and now we have to start over and move into a whole nother tool. The good news is that we don't. We're going to use that properly specified model that we found using OLS in GWR. And it is important to note, we're a little bit conservative here when it comes to this, but it's really important to find a model that you can trust using OLS, because OLS has all of those really strong diagnostics. Geographically weighted regression does have some diagnostics, but there's a lot less diagnostics than there are in OLS. And so we feel really confident when we find a properly specified model using OLS and then moving to geographically weighted regression to improve our model and to explore the spatial variation in our relationships, as opposed to just jumping into GWR because you can't find a properly specified model using OLS. But that is kind of a conservative approach to things. So what is geographically weighted regression? How is it different than OLS? So they are both linear regression methods. The big difference here is that ordinary least squares regression is a global model, and GWR is a local model. So OLS, we've spent quite some time seeing that equation, right? That one equation represents everything in OLS. It is the result of your analysis in a lot of ways. Each variable has a single coefficient for the entire study area. So what that means is that relationship is fixed everywhere. GWR actually creates an equation for every single feature using nearby features. So the coefficient in one part of your study area might be different than the coefficient in another part of your study area. So that looks a little bit like this. So each feature gets a separate equation based on its neighboring features. So that one feature gets an equation, and every other feature gets an equation. So the idea here is, again, it's Toblers Laws. The idea that things that are closer together are more related than things that are farther apart. So my neighbors are can do a better job of modeling my value than features very far away from me, especially if we believe that we're modeling something that might actually change over space, and a lot of things do. So what this allows us to do is to see how those relationships really can change. When I was looking at childhood obesity, one of the things I was really interested in was access to healthy food. And I was modeling that using distance from the supermarket. And my study area was Los Angeles County. And what I found was that in some parts of Los Angeles County, like South Central Los Angeles and some of the lower income areas, being close to a supermarket actually was related in the way I expected to childhood obesity. The closer you were to a supermarket, the less likely you were to be obese. But in Beverly Hills, I found a completely opposite relationship, which in retrospect makes a lot of sense, right? You don't buy a $10 million mansion next to a Stater Brothers, right? That would be, I mean, I don't know what you do when you buy a $10 million mansion, but I'm assuming if I was buying one, I wouldn't want it next to the Stater Brothers. Beautiful Malibu Hills or something. So these, in Beverly Hills, it's actually the people closest to the supermarket that are the lowest income, less educated, all of those other factors. And in those locations, the closer you are to the supermarket, the more likely you are to be obese. So that the relationship between those variables actually flipped depending on where you were in my study area, because those places had such different characteristics that that one variable couldn't be held kind of constant across the study area. So geographically weighted regression allows those relationships to vary across space. So we're going to see GWR in action.
Okay, so like Lauren said, we're not actually starting over. We're going to use those same variables, but this time we're going to get some really interesting spatial outputs that help us understand how the model predicts over space. So our dependent variable, our costs, and then our explanatory variables, hospital beds, readmission rates, imaging, distance to Houston, and dehydration. So distance to Houston, something that we didn't actually end up talking about earlier. It's actually measuring how far each of those referral regions is from Houston, because Houston has, I believe, the largest medical center in the country, the world, something like that. And so it's what we call a spatial variable. And a lot of times when you're trying to model something and you're not finding a properly specified model, you might consider including a spatial variable, measuring distances between things, and adding that into your model to kind of capture some of that spatial component, because things do vary over space. Okay, so I'm going to go ahead and run this. Okay, and we see that our adjusted R squared is now 0.82. Did you include all the variables? Let's try that again. Hospital beds, readmission, imaging, Houston, dehydration.
Wait, is it readmission?
No. It's
PQ. Oh, evaluation and management.
Yeah. All right, that's better. Now our adjusted R squared has gone up to 0.879, which is even better. But this report has a lot less information than the OLS output. So really, we can't trust this unless we've already found a properly specified model using OLS first. This can help improve that, but we can't trust that R squared alone if we haven't passed the other 6 checks, and we can't really check those things running just GWR. So first we have an output here of our residuals, but we can change the symbology to actually see how those different equations vary over from feature to feature. So we can map our coefficients and see the strength of the correlation that these variables have over space. So let's take a look at imaging. And I'll change the symbology here.
I cannot believe that projector. Wow.
Oh, should I choose something dark maybe? Yeah, that's all right. Okay, so we're looking at the coefficients and how they vary from place to place. So we see that in this darker area, imaging events are a stronger predictor of Medicare spending than in these lighter areas. So that really helps us focus any remediation efforts. It helps us target how to solve these problems, how to address the Medicare spending issue. Let's take a look at one more. Dehydration. I'll change that. Red color. Okay, so now we see, again, it's very obviously a spatial problem. Over here, dehydration is a really good predictor of Medicare spending. Over here, not as strong. So it doesn't really mean that we have more dehydration in the dark area, and it doesn't really mean necessarily that we have more spending in that dark area. It just means that in this area, those numbers are more strongly correlated. They rise and fall together more than they do over here in this lighter area. So if we wanted to maybe start some outreach programs to educate the senior population on how to stay hydrated, we could focus that over here, because really resources are never unlimited. We never can just implement something everywhere. So this really helps us identify where we'll get the most bang for our buck, if you will. So I think that GWR is a really interesting tool. And even if you don't find a properly specified model, it can be used for other things. So we cut the study area down to just this cluster. We used a hotspot analysis to choose a subset of the region to run this analysis on. Sometimes I'll run GWR against a couple of variables to help me kind of cut down the study area, because it's really going to be difficult to find a properly specified model for the whole entire country, because there's going to be too much variation in how these variables interact from place to place. So if I had run it over the whole country and I found an area where one variable was strongly correlated, maybe I could cut that area out and throw some other variables over there to see if I can find a model in a subset of the features. So back to the slides.
All right, so we talked about the fact that GWR is a local spatial regression model. One of the things that is important to note is that you use the same variables that you use in OLS with a couple of caveats. One is that if you do we include spatial variables all the time. Usually our spatial variables are things like distance from highways, distance from hospitals, distance from parks, distance from supermarkets, those kinds of things that show a lot of variation over your study area. So you can leave in those spatial variables. But if, let's say, you include a spatial regime variable where you have a whole chunk of the area that is urban, and then you put the rest of them as rural, and you do a 0, 1, those are variables that you are going to want to drop. The way that GWR works is by looking at each feature in relation to its neighboring features when it calibrates the model. Well, if all your neighbors have the exact same value as you, what happens is essentially GWR can't solve. It's doing some crazy matrix math, and the matrix just won't invert. And it just says, nope, sorry. So, but the good news is that because of the nature of the tool, it often will essentially take care of those dummy variables for you. It's going to find those regimes in the data because it's looking by neighborhoods. You also, in the same way, just don't want to include variables that have very little variation. So one thing that we run into sometimes is people have kind of surface data, raster data, and they want to sample it or kind of turn it into points to run regression analysis. And you have to be really careful when you do that, because if you just turn every single pixel into a point, pixels that are next to each other are going to have the exact same values, or there can be very little variation in large swaths of your data. So you're going to want to be careful that you're picking kind of representative locations, because if you just have everything, you're going to have way too little spatial variation in those values for the model to solve. You'll just have a lot of what we call local multicollinearity. And you can actually test, one of the values in the results of the analysis is what we call a condition number. And when that condition number is above 30, what it's telling you is that you do have a lot of local multicollinearity. It's kind of like, how hard was it for this model to solve? And when you have numbers above 30, it tells you the model was pretty hard to solve in those locations. And so you might want to think about what variables would be exhibiting that kind of local multicollinearity. So we do have to define when we run GWR what it means to be local. but what it means to be nearby. Now there's defaults, and the defaults are actually in this case really good. There's two parameters that you have to think about. There's a kernel type and a bandwidth method. The kernel type, you have two options. You have a fixed option or an adaptive option. Fixed essentially is going to choose a distance and use a moving window distance to create that model. Adaptive is going to use a number of neighbors, which means the number of neighbors will stay constant, but the size of it is kind of adapting based on how many, sometimes 16 neighbors could be this big, sometimes over here 16 neighbors will be smaller. So it's using a neighbor based on number of neighbors. Then for the bandwidth method, essentially with these are options that you can use to let the tool decide what the best fixed distance is or what the best number of neighbors is. And there's two methods that you can choose from. One is called AIC and one is called cross-validation. And both of them will essentially try to optimize the number of neighbors or the distance so that you have a model that is unbiased, that's doing as good of a job as possible as far as the model performance goes. So you can also, if you have some meaningful reason to do so, provide a distance yourself or a number of neighbors if you want to. So that's another option for the bandwidth method, but just something to think about. But the default itself is good. The AIC and the cross-validation do a really good job of optimizing what the appropriate distance or number of neighbors will be. So like Flora mentioned, there's other things that we can map too. So for instance, if we calculate a condition number for each one of the features, we can actually map those condition numbers and see where is that local multicollinearity. Where is the model having a hard time solving? Or we can map the coefficients like we talked about. We can map those R-squareds. Obviously, the residuals are the output of the tool. Those get mapped automatically. But all of those attributes are just part of the output of GWR, and they're just all these things that we can map. So GWR, again, can be a really powerful exploratory data analysis tool for you to explore those relationships, explore the spatial variation in those relationships, and learn a lot about your data that way. So miraculously, we finished with time for questions this time, even though we're talking about regression analysis. So we can definitely take questions, and before I say let's take questions, I do want to remind you, please fill out a course survey, and when you're done with it, leave it on that back table there. Our offering ID is 1230. We really appreciate your feedback. We use it to get better every year, and we have more sessions. EsriURL.com/spatialstats is our resources page. We'll be updating that with all of these workshops as we get them all packaged up for dissemination. We're also going to give them to the conference organizers so that they can put them up on the website. But you can always find the latest resources at EsriURL.com/spatialstats. That's got hands-on tutorials with data. It's got links to free live training seminars and workshops that we've done in the past. We'll put the links to these workshops when they go up. There's links to some of our favorite documentation, including that regression analysis basics workshop. So there's a ton of resources there. And Flora and I are also, of course, resources to you. I say it every time, but it's true every time. We work really hard to build these tools, but they're only powerful because of the things that you guys do with them. So we are really happy to help however we can. And we love hearing just about, if we love getting your questions and the problems you're having, but if every once in a while you do something really awesome and want to tell someone about it, we're always happy to listen because I love to hear about the things that people are doing with these tools. I find it very inspiring. You guys are doing amazing things. So thank you. We have some time we have 10 minutes for questions, or thank you anyway. Yeah. So the question was, would we recommend the AIC or cross-validation over choosing a distance band using a semi-variogram? Yes, I would. And the guys who on the geoprocessing team who are responsible for the geostatistical analysis, our implementation of the semi-variogram, they implemented both the cross-validation and the AIC method in GWR, and it's pretty awesome. So I always just go with what the tool tells me to go with. Yep. Yes. So So the question was, do all of the explanatory variables have to be in the same file? The answer is yes, they all have to be in the same data set. Just on a related note, even though it is not your question at all, but since I have the time to talk about it, one thing that we often get asked is, we spend a lot of time talking about this, how important it is to not have spatial autocorrelation of your residuals. That does not mean that your explanatory variables or your dependent variable can't have spatial autocorrelation. They can be and almost always will be spatially autocorrelated. That's kind of the whole point, right? We're trying to understand the spatial autocorrelation. So the only requirement is that the over and under predictions are not spatially autocorrelated. That's an important point, I think, because your inputs don't have to be, yes. Why? Spatially autocorrelated. It is just one of the underlying assumptions of the regression method. If you read like the original paper on ordinary least squares regression, it just means that your model is biased and that you're missing key explanatory variables. What's that?
And then it predicts well in some areas.
Right. It'll be well, and the other thing is, in one area you'll be doing well, and then in other areas you're doing really badly. So it's like the R squared might be on the high side, but there's a whole chunk of your study area where you're not doing well. It just means you have an unstable model, and you just can't trust the results. Spatial autocorrelation is one of those things that is often forgotten about, but it's critical. We've seen, especially when we haven't found a properly specified model, you throw in a variable and signs will switch. I mean, crazy things happen when you don't have a properly specified model.
Would you recommend checking if it's variables are spatially autocorrelated?
No. I would not. You don't have to check it all if your variables, the input variables, are autocorrelated spatially. Sorry. Yep. Yes, absolutely. These tools have been in the software since 9.3, so you have them. They're all there. We're always going to be changing them. We don't have anything currently planned in terms of updating these tools that I can think of off the top of my head, but we're always, we've got a long list of things to do and like 3 open positions on our team that we want to fill so that we can do that long list of things. So we have a lot of plans. Yep. So the question was, do you always need to move to GWR, or can OLS tell you in some way that there's no local variation in your data? That's a really good question. There is a diagnostic. Let me just go to the diagnostics page quickly. There is a diagnostic. Come on. It's called the Kernker statistic. And it's there on the bottom. It's the Broich-Pagan statistic. And essentially that is testing to see if there is any kind of, it's testing for non-stationarity is what it's testing for. And so if that is statistically significant, it's often an indicator that GWR will improve your R squared. But I'm a little biased in that I would say I always go to GWR, even if that's not statistically significant, because there's no harm in going to GWR, and I'm always interested to see even the very minor variations in the relationships, or just to map some of those other values that can be really interesting. But there are times where GWR doesn't improve the model because there just isn't a lot of variation in those values. But most of the time, especially when you see that Broich-Pagan statistic is significant, you'll almost always find that it improves the model. But that's a good question. Yep. Is there anything in this?
So it's great that all this is in there, and I've always said that Geographic recommending things for non-statistical analysis, but let's say you have 5 variables that are collinear, and you want to shrink it down, instead of just using one proxy, you want to create a factor that.
Sure.
Yeah. Is software knows that yet?
We do not have any factor analysis. There's no way to do that right now. And we have tools that do similar things in terms of data clustering, but not to create factors. And But you can absolutely create factors and use them. I know when I did my analysis, I did experiment a little bit with that. I don't love the factors because then I can't really, they become these abstract things that, yes, they can help me find a properly specified model, but then it gets to the, if my whole goal is prediction, then that's fine. And all I want to do is just predict what a value is going to be based on these factors. But if I want to, if it's about the relationships and being able to say something about those relationships, then I don't love factors. So it just depends on your reasoning for doing it, but you could definitely create them and use them in the software. Yep. So that's a good question. It is, we'll dig a little bit deeper into certain things. We walk through an analysis. Flora's going to show a couple of things that we can use GWR for that are kind of outside of this realm. There is going to be, I don't want to say there will be overlap. We're not going to be like showing the same slides. We're not going to get into the depth about regression analysis. We're not going to get into the depth about cluster analysis. It's more going to be just walking through an analysis. I'd say if you've gone to all of the other ones and you just love spatial stats, you'll definitely get new things out of it along the way. But it's a real challenge for us because we want to make each one stand alone and then simultaneously create some sort of a progression so that people can come to all of them. So we are doing our very best to make that possible in the last one too. So I know it's not that late though. So it's like 1:30, right? It's not like the one that ends at 5 o'clock. Our one tomorrow ends at 5 o'clock. So the people in that one are like real troopers. That's what I have to say. Yep.
What is the type of geographic unit play into the GWR as far as whether you have different size units, census tracts are small and big, and different sizes of counties?
Sure. So the question is, how does the size and the shape and of our polygons impact our output? And I guess I would say it impacts it like it impacts basically everything we do. The modifiable aerial unit problem is a huge problem. I mean, it's just something you always have to be aware of. It's something most of the time there's nothing we can do about it. But being aware of it is important. I don't think there's nothing I've ever read as far as critiques of GWR, and as you can imagine with every method that exists under the sun, there's always a critique. There's always opinions about methods, and some people love GWR, some people don't love GWR, but none of them I've ever read are at all related to issues with the size or shape of the polygons. So I think it's really just kind of your standard, make sure that, or at least acknowledge that the way that you're bounding your data can have an influence on what you find. And especially, I mean, the one thing that I think about that there is something that you can kind of do about is do the polygons that you have, does the data that you have support the scale of your question? Because if you're looking for local variation and you're running analysis on counties, I mean, good luck, right? I mean, if it's all you have, it's all you have, but so if that's all you have to think about what questions you can actually ask with that data. Because you can't ask all questions with all data. And county level data, I mean, Los Angeles County is a country, basically. It has the GDP of many countries. Sorry, I'm a little bitter about my study area. But it is like its own country, and that's true of a lot of counties. So that is something to think about, is just what questions can I even ask with the data that I do have. Yep.
Have you handled spatial data density, where I don't know if you had counties there before, it's called for population, where some of the statistics might have like tended towards the mean, but in like rural areas you might have higher variability?
Sure. So how do we account for population? I mean, in this case, the values, like if we're looking at, if the thing we're trying to model is a count variable, there is always a population variable included in the model, and it's usually most of the time, if we just included population to explain a count of something like incident related, population is going to get us half of the way there because it's explaining a lot of why so many things happen in those locations. So we can take it into account that way, or make sure that the variables that we're including are, the meaningful variables that do reflect taking that information into consideration. Like if you think that a variable is related and you have the option, a lot of the business analyst data that we can get it as a count, we can get it as a rate, we can get it as an index. And what I love about exploratory regression is we can kind of play around with which one of those is going to do the best job predicting, because they are all getting at it in a different way. But yeah, and that's also why I love OLS, because these checks make me really confident that if that variable says it's statistically significant, we don't have spatial autocorrelation, our residuals aren't biased, we have a higher, once I've gone through that, I feel really confident that I'm dealing with a lot of the issues that are really common in these kind of models. Actually, we kind of want to do something fun. Can we do a selfie? Will you guys be in our selfie? Okay. We should have done it in every one of them.
I know. Also, everyone's left, so now we.
It's okay. It's okay. Well, you
guys
are the winners.
Okay, wait. I turned it around.
Wait. Yay. Thank you, guys. Thank you.